Quark-Gluon Plasma. This is the topic of discussion in today's lecture. And of course there is quantum chromodynamics. You know, quantum chromodynamics, this is studied under the subject heading of particle physics. In particle physics you would find a standard model, and quantum chromodynamics is a key component in the standard model of particle physics. So to test quantum chromodynamics, which is nothing but the study of strong nuclear force. You know that there are four fundamental forces such as strong nuclear force, electromagnetic force, gravitational force and weak nuclear force. So out of that, in number one position there is strong nuclear force, and that strong nuclear force is studied under the subject heading of quantum chromodynamics. And to test quantum chromodynamics there is one requirement, means you need to do experiment. And for that experiment, what is the requirement? The requirement is the creation of Quark-Gluon Plasma. Quark-Gluon Plasma, this is a state of matter. And this state of matter was created just after the Big Bang. Just after few microseconds, this state of matter existed. Yes, I am talking about Big Bang, just after the Big Bang, only for about few microseconds. This state of matter, I am talking about the state of Quark-Gluon Plasma. Here quark and gluons, they are not bound together. You know that in neutrons, protons, neutrons, then other hadrons. In those particles, quarks and gluons are bound together. But in case of Quark-Gluon Plasma, quarks and gluons are not bound together. They are free to move. Those are unbound state of matter. Yes, they can move freely inside the plasma. And here the temperature requirement is of the order of trillions degrees of Kelvin. Actually, whenever we talk about trillions of degrees of, then in that case Celsius and Kelvin become the same. There is almost no difference. Anyway, normally Kelvin, this temperature, this unit is used in the discussion of such things. So the temperature requirement is of the order of trillions of degrees Kelvin, and that temperature was available during the first few microseconds after the Big Bang. So that thing we are not going to create here, but in our laboratory, you know, there is Large Hadron Collider, or in brief known as LHC. Again, there is RHIC, which is known as the full form of RHIC. RHIC is Relativistic Heavy Ion Collider. So in these two colliders, this experiment can be done, means can be conducted. Experiment on Quark-Gluon Plasma. Means first you have to create Quark-Gluon Plasma, then you can do the required experiment related to quantum chromodynamics. Okay, so here normally lead or gold, these elements are used. Okay, gold or lead means heavy elements. You know, the name of RHIC, full form of RHIC is Relativistic Heavy Ion Collider. So here gold and lead both are heavy ions. And the speed, nearly the speed of light, equal to the speed of light. Nearly equal to the speed of light means it is less than the speed of the light, but the difference between the speed of the light and between the velocities or the speed of these particles inside those particle accelerators are almost same or nearly same. So particles smash together at such extreme velocities, and therefore such high temperatures of the order of trillions degrees of Celsius or Kelvins are created. Okay, and physicists get the facility of observing Quark-Gluon Plasma. This is very interesting because normally we cannot see gluons and quarks to be free. They are always bound together inside any matter because any matter is composed of neutron, proton, other hadrons. Okay, and always quarks and gluons are bound together. None can observe them to be free or to be separated. Okay, but if you can create this plasma state, which is known as Quark-Gluon Plasma, so in that case you can observe. Okay, here the viscosity of the plasma becomes very small, means it becomes minimum. So they can smoothly flow. So this is known as, this state is known as the state of perfect fluidity, means perfect fluid. This can be called as perfect fluid. Okay, so the main purpose is to create this state. Again, so one purpose is to study quantum chromodynamics. Another purpose is to study the Big Bang itself. Because just the first few microseconds, this state was there during the Big Bang. Okay, so if you can create the same thing, same environment, same matter inside your laboratory, then studying those things, we can easily predict what happened during the Big Bang. And one more thing I should mention here, that study of quantum chromodynamics is very complex. It is highly nonlinear in nature. Okay, so and mathematical complications are there, and those things can be solved or can be predicted accurately or confidently if you can study this state of matter precisely. Okay, anyway, so this was all about the topic Quark-Gluon Plasma. Okay, so this is the end of this video. Thank you for watching this video.